Start recording here. There we go.
And Mr. Edelman, I'm here, but I'm driving. Okay.
I see you, John E.
Yeah.
There you are.
Yeah, I'm coming back from Ellicottville, but I'm listening though.
Yeah, well, don't get into a crash.
Well, all right.
This is like, oh, here we go. I was going to say, where is everybody else? We haven't had a group quite this small ever, I don't think. But all right. Open up the floor for questions.
I have one on the cardiac chapter.
Okay, great.
So it's talking about the polarization of the atrial cells.
Yep. And
polarization occurs when like calcium ions are going in and out or something, right?
Let's talk about that section.
Yeah, because that was like kind of overwhelming for me to read because it sounds like, you know, every time the heart pumps, these cells are going back and forth in charges. So I don't.
Yeah. Okay. It's not as bad as you might think it is. But I'm pulling it up as we speak, and we'll talk about the cardiac conduction system. It's really, really interesting. This is a big PowerPoint, so it's taking just a few seconds to load up here. All right. So let me try to share my screen. Do you see the PowerPoint now? Okay. So this particular section starts here on slide 43, I think, right? Okay. So everybody's hopefully familiar with the anatomy of the heart. You can see again the tricuspid valve here. Here's the bicuspid valve, the papillary muscles down below, the chordae tendineae here, right? The superior and inferior vena cava, interventricular septum, et cetera, right? Everybody good with that?
Yeah.
Okay. So if we look in the upper superior portion of the right atrium, we have a little piece of tissue that is part cardiac muscle and part nerve tissue. And it's called the Cynoatrial Node, or SA for short. So SA stands for Cynoatrial, S-I-N-O-A-T-R-I-A-L, all one word, Cynoatrial. And as you can see, this is affectionately referred to as the pacemaker because it sets the heart rate. And so this little piece of part cardiac muscle, part nervous tissue will initiate and distribute impulses that culminate in a heartbeat. So every time your heart beats, and we'll talk about that process in a minute, but every time your heart beats, it occurs as a result of this little piece of tissue sending out impulses to the four chambers of the heart. Okay. If you need a pacemaker put in you, it's likely due to the fact that some of these pathways that you see here shown in yellow are not working properly. And so the normal SA node isn't functioning the way it should. So you need an artificial pacemaker. It's typically placed just underneath the skin. And then there are electrodes, or I should say leads, that will snake their way through blood vessels to different parts of the heart, depending upon where the problem is. But it could very well snake to this particular region. So the artificial pacemaker picks up where the natural pacemaker would work. Okay. All right, but we're going to assume everybody's healthy, heart's working fine. What occurs? All right, so here the impulses originate, and you can see in yellow the pathways that the impulses take initially are through the walls of both the right and left atria. Okay. Now, what do you think the atria are going to do in response to those electrical signals? What would you do if you were the right atrium? Well, come on, this isn't rocket science. If you deliver an impulse to a muscle, what's the muscle likely going to do?
Contract.
Right. And so that's what happens to these atria. They contract together upon stimulation from the SA node. We refer to that as atrial systole. Maybe you've read about that in one of the earlier slides. Okay, so the word systole, S-Y-S-T-O-L-E, is just a fancy word for contraction. And relaxation, we use another fancy word for that. It's called diastole. That's spelled D-I-A-S-T, I'm sorry, D-I-A-S-Y-S-T-O-L-E. Diastole, it's a long E sound at the end. Okay, so we've got the two atria undergoing systole or contraction upon stimulation by the SA node. And you know that when the atria contract, the AV valves open and the blood flows into the two corresponding ventricles, right? Hopefully you know that. Now, when the impulse gets to the base of the right atrium, very near the interatrial septum, there's another piece of part nervous tissue, parts cardiac muscle, called the AV node or Atrioventricular node. So we talked about AV valves, right? Same word, atrioventricular node. And you might, if you look really close, you see where they say junctional fibers leading to the AV node from the SA node, and you see how their diameter is a little bit smaller than some of these other diameters of these pathways, these nerve pathways. And the reason for these junctional fibers being so small, which I put, of course, here in the blue box, is to delay the impulse just a little bit before they get here. And you'll see why in just a minute. You have to delay the impulses just slightly to allow for the atria to undergo systole and allow the ventricles to undergo diastole. If there was not the delay, then all four chambers would undergo systole at once. And that would not be conducive for good blood flow. So that's why these junctional fibers are there. They lead into the AV node. They're very narrow in their diameter, and they slow the impulse just a little bit, enough to allow the atria to undergo systole and the ventricles to undergo diastole. Okay, from here, from the AV node, notice there's just a single pathway that the impulses then take down the superior part of the interventricular septum, and then it splits, as you can see here, into what's called the right and left bundle branches. The left bundle branch will come down and then travel into the wall of the myocardium here of the left ventricle, and even up into the papillary muscles. And the other right bundle branch is going to come down the other side of the interventricular septum and make a curve near the apex and head on up and infiltrate the myocardium of the right ventricle and also the papillary muscles. What do you think the ventricles are going to do in response to those stimuli? You said contract, you were right. Okay. When the ventricles contract, the blood from the right side goes into the pulmonary trunk and goes to the lungs, And the blood from the left side goes where?
Out into the body.
Into the aorta and throughout the body, rest of the body, right. So do you now understand why we had to delay the signal here just a little bit, the impulses?
Mm-hmm.
So it gives the time for the ventricles to relax before they immediately do what?
Fill up again.
Contract.
Well, they're going to fill up as they relax, but they're going to contract right afterwards.
Okay.
All right. Now think about it. As the ventricles are contracting, guess what the atria are doing?
Relax.
They're undergoing diastole. They're relaxing in preparation for the next cardiac cycle. You see what I'm saying? So what governs the contraction or systole, as well as the relaxation or diastole, is this cardiac conduction system. So the ventricles are the first to contract. At the same time the ventricles relax, then the ventricles contract in preparation for atrial relaxation, and then we repeat the process again. So if you have, let's say, a heart attack and you build up scar tissue, let's just say, for example, here in the upper right bundle branch area, and the impulse cannot proceed through it like it normally would because of the scar tissue that occurred as a result of the heart attack. Do you see how that could potentially impact how the right ventricle works? Because you're impacting the pathway that the impulses have to take to stimulate that part of the heart. Or what if you had damage up here to the AV node? Holy moly, then you're impacting everything downstream of it potentially. So there's all sorts of heart anomalies that can impact different parts of this cardiac conduction pathway and in turn influence the way in which the heart functions. And I can't speak to all the different pathologic conditions that exist, but there's a whole bunch of them, and I'm sure the book that describes this is probably about yay thick, just on heart problems, just on the cardiac conduction aspect of this. Okay, so let me just stop here and ask, are there questions? Makes sense? Better than it did, Paige?
Yes, thank you.
Okay, so now let's talk about the ECG or EKG and see how that relates to this cardiac conduction system. So this next slide is simply a pathway that the impulses take. So this is nothing new. We've talked about this. Oh, let's mention this too before we get to the ECG. This is really, really interesting. Here, of course, we see the ventricles down below. Here's the auricles of the atria. This, of course, is the aorta. Here's the pulmonary trunk. Here's the left pulmonary artery. Here's the right pulmonary artery. And, of course, the superior vena cava coming into the right atrium. And the pulmonary veins, of course, shown here as well. I want you to note here in the ventricle walls how we have this kind of interesting patterning of how the cardiac muscles, fibers kind of orient themselves. So this is described as, they're describing the cardiac muscle as John, I'm going to mute you because we're hearing some sounds. It's either his breathing or the cars going by. I'm not sure which. So we've got this interesting, unique patterning of the cardiac muscle fibers, and they're oriented in what are called whorls, W-H-O-R-L-S. It's a funny term, whorls. And the reason that this patterning is kind of interesting and important is because when the ventricles go to contract, right? Once the impulses get down to the apex and then they start working their way up into the ventricle walls, right? We know that that's going to result in contraction. Well, the contraction begins here in the apex and it works its way northward, if you will, just like the impulses, start here and then they work their way up into the ventricle walls. That means that when the heart contracts, when the blood gets ejected from the two ventricles, it gets ejected from the apex upward. Here's the analogy I want you to think about. If I gave you a wet washcloth and I asked you to get as much water out of the washcloth as you can, what would all of you do instinctively? You would wring the washcloth, right? Well, I want you to imagine the hard ventricles here as the wet rag. If you want to maximize blood ejection from the ventricles, the best way to do that is to wring the heart from the apex upward. And that's really what happens. If you were to see a heart beating in somebody's body, it wouldn't twist as much as a rag would twist, but it would, you see a discernible twist as due to the whirling here, the patterning of the cardiac muscle fibers in the ventricles. It's an evolutionary thing that maximizes the ejection of the blood through the pulmonary circuit and the aorta. I think that's really cool. Okay, so here's the ECG or EKG. This is the old Germanic abbreviation with the K versus the C. It stands for electrocardiogram. And maybe you've had these taken before. A typical ECG taken at the hospital would involve a 12-lead system. They take these disposable electrodes and they place them on your chest and your back, right? And they'd hook up little electrodes. It doesn't hurt. You just sit there and they run the strip. Then they pull these things off and toss them. They're just disposable little electrodes. But the ECG has a very interesting waveform to it. You can kind of see 5 of them here. Before we get into different aspects of the ECG, there are these 2 terms that we want to sort of define. And this gets back, I think, Paige, to your question about ions, maybe. Depolarization and repolarization. These words you're going to hear about next semester when you take A&P2, if you take A&P2 in the nervous system. When we talk about a nerve impulse being generated along an axon, you're going to be hearing about this initial depolarization of the membrane, followed by repolarization of the membrane. And so they're terms to describe electrical changes that occur along a membrane, plus and minus charges, basically. And this is due to the migration of ions, in this case, sodium, into the cell. And I'm not going to get into that right now. You don't need to know it for the test. But just understand that these 2 words describe electrical changes due to ion flow, basically. I want you to also connect depolarization to systole, because depolarization leads to systole. What is systole? We said it's a fancy name for what? Can you hear me? Okay. there's no response. Systole is a fancy name for contraction. Okay. So if depolarization leads to systole, guess what repolarization leads to? Don't say relaxation.
Oh.
What's the fancy word, Sadie?
Didn't you just say it? The one that starts with a D?
Yeah.
D.
What is it? Say it.
I can't remember.
If you say it, you'll remember it. Diastole.
Diastole. Okay.
Yeah. Okay. So depolarization leads to systole. Repolarization leads to diastole or relaxation. And that'll be easy to remember. Just remember, repolarize leads to relaxation. Okay. I can't help you with the DE leading to contraction or systole. There's no obvious similar letters there, but okay. So knowing that, we can now take a look at an ECG and see where these 2 processes are taking place within the heart during the cardiac conduction pathway. So here we are, back to the heart. You see the SA node I've noted here in green. You see again the two atria, the two ventricles. Here's the pulmonary trunk. Here's the aorta. Nothing new here. So we said earlier that this SA node is where impulses originate and are distributed, right? And here they are beginning to be distributed. So we're seeing them begin to get into the walls of the right atrium here. So this is depolarization. This is the excitation of the right atrium initially. But again, where's the yellow going to go next in the next slide? Any idea?
The right ventricle.
No.
Nope.
Nope.
It's gonna go on the left side to the other little I don't know the names.
Yeah, you
it's
do.
like
The left atria.
yeah.
Atrium.
Atrium. They're both, two of them are atria, right?
Right. Singular atrium, plural atria. So there you go. Now the left atrium is being depolarized. And once those two atria are fully depolarized, that is going to be picked up on the ECG as the P wave, the first little part of the EKG. This, we said, leads to atrial systole or contraction. Okay. So the P wave of an ECG is depolarization of both atria. This is
And now is that the bump on the line, is that much smaller just because the atria are only pumping blood into the next chamber? They're not like, trying to get out to the lungs or?
No, that has really nothing to do with the size of this little bump. Okay. So this y-axis doesn't indicate milliliters of blood being pumped. This is an electrical signature.
But is that why, like, it doesn't need as much of an electrical impulse to, contract those?
No, I don't think so. I don't know how to answer your question. I think I understand what you're asking, but
I'm just asking, like, why, like when the ventricles squeeze, the line is like crazy, and when the atria squeeze, they're just like little.
I guess I would simply answer it as follows, and that is that atrial depolarization is just not a super significant electrical event like depolarization of the ventricles will be. You might think of it as, well, we're just sending out impulses from the SA node through the walls of the atria. Well, in a few seconds, we're going to have to send a bigger impulse down here, and then it's going to curve up here and curve up here and go up into the papillary muscles. It's just more of a significant process. That's how I would look at it. That's a very simplistic answer, and I'm not sure it's super accurate, but I think for you, it's probably, maybe that'll help.
No, that makes sense. Thank you.
Okay. All right. So I want to just underscore this idea that this P wave, which we said was depolarization of the atria, this is not a measure of the mechanics. This is a measure of electrical impulses. Nonetheless, what does this lead to mechanically? Atrial systole. Okay. Again, I just want to underscore this so you're super clear in your mind. The P wave is measuring electrical activity that leads to a physical mechanical event. When I say mechanical, you know what I mean? Something you can visually see, the muscles, the atria contracting. Can you see this? Well, I can see it on ECG, but can you see these impulses travel through the atria? No, you can't see that. You can measure it if you put leads on you, sensitive enough leads, you can measure that as a P wave. Now, again, millivolts, this is thousandths of a volt. We're talking about something less than a tenth of a thousandth of a volt. These are very small electrical events, very small, very important, but very small. Okay, now where's this yellow going to proceed from here? You can tell me. It's going to proceed into the AV node and then down the interventricular septum and then into the right and left bundle branches and ultimately into the ventricle walls, right? Just think back to what we looked at 3-4 slides before. And you can see how that's beginning to happen here in the ventricles. They're starting to be depolarized. They're not fully depolarized yet, but they're beginning to be depolarized as a result of that process I just mentioned a second ago. Look what's happening up here in the atria, though. We've got them colored green. Green represents repolarization. What does repolarization lead to? Relaxation, right? Okay. Next, we fully depolarize both ventricles. And so once we start the repolarization of the atria and the depolarization of the ventricles, we have what's called on the EKG, the QRS complex. This is P. This is called Q. I'll go back here. Here's Q. Here's R. And then we go back down below the Q. This is called the S part of the QRS complex. This is what Paige was talking about a second ago, this really big upswing and downswing of the ECG. So what is the QRS complex? It's two things. It's depolarization of the ventricles, and what else? What do you see here in green?
The relaxation of the atria.
Well, that's the mechanical process, but this isn't measuring that. So what's the answer? Depolarization of the ventricles and repolarization of the atria. Okay, now you're right, Sadie. It leads to relaxation. I'm not arguing with you there, but I got to underscore this. This is not measuring mechanics. This is measuring electrical activity that leads to mechanics. So if I ask you on a test, what does the QRS complex represent? You really should not write atrial relaxation and ventricular contraction. Some books would tell you that, but they really should tell you that the QRS complex represents both ventricular depolarization and atrial repolarization.
Oh, okay.
Those events lead to ventricular contraction and what?
Relaxation.
Atrial relaxation, right. Right. Okay. So the last event in the ECG is called the T wave, and there it is coming up. And T wave represents repolarization of the ventricles. So we're going to repolarize them. And then we can start all over again with another ECG. So this is the beginning here, and here's the ending of the entire ECG PQRST waveform. And every time your heart beats, it does so in response to an ECG.
So like, what would that look like if you had an extra heartbeat?
By an extra heartbeat, you mean like a little flutter of your heart?
Yeah, because like I had to go and done because I had like a popcorn heartbeat and they call it like an extra one. Like I don't know.
Are you saying your heart rate was double the norm?
That's what they said. And then I had to like wear a thing for like a day.
Yeah.
And like when I was like physically active, then it went like back to normal. But like normal like heart rate. They said like a popcorn heartbeat. I don't really know.
How old were you when you had that?
That happened last year.
Oh, so you were on telemetry, yeah, had hooked up to a machine and for a day.
Yeah.
I don't know. I'm not familiar enough with what that refers to. You probably don't have any ECGs laying around your house on that, huh?
Oh.
It'd be interesting to take a look at those. Now you wish you probably had access so you could look at
Right.
them and see how they compare.
Mhm.
Did they say what was going on? I mean, obviously it remedied itself. Okay, you haven't had any issues since then?
Yeah, no, they just said like sometimes it happens. Like it like they didn't fix it or anything. It
Yeah,
just
that just happened. Huh? And what spurred you to get tested? What was the, did you have?
I was getting a physical done just for sports, and
Oh,
they finally noticed it, I guess, like years later. So yeah,
huh. So you
I
had it your
just
whole
feel like
life?
what?
You had it your whole life, you think?
Yeah, and they like just noticed it last year. I had like a physical, and I had to like stay overnight, and they had to like keep in like an EKG on me, and then like I like went to basketball practice, and then they like read like my things, and like I had to like stay the night then later. So like I left and then
Yeah.
came back.
Uh-huh. Yeah, interesting. Yeah, I don't know.
Cheers.
If we were to have met in lab and not had COVID restrictions, you would have worked with a partner and we would have measured each other's ECGs using a small handheld computer with some electrodes that we would have put on your arms, your wrists, and your ankles. And we would have measured some ECGs, and we would have not only looked for the different waves here, like we just described a moment ago, but we would have had our little handheld computer measure certain intervals or time frames within the ECG. And this would have been particularly interesting for you, Sadie, because then you could have not only compared, your ECGs, but the cardiologist would be interested in whether your time frames here within the ECG fell within normal parameters. So for example, this PR interval is from the beginning of the P wave, as you can see here, to where the R begins. They call it PR, but it's really kind of like P to Q. Don't ask me why they call it PR, but they do. And that should be somewhere between 120 and 200 milliseconds. So 0.12 is the same as 120 1,000ths of a second. So milliseconds is often what they use. You can use seconds too. The QRS complex, which is from Q to the end of S, that should fall somewhere less than 120 milliseconds. And then this QT interval from Q here, beginning of Q, to where T comes down to the baseline, this should be between 300 and 400 milliseconds. And so again, in addition to measuring the actual waveforms, the computer would have calculated these various intervals, and we would have looked to see whether your PR interval fell within the normal parameter and so on and so forth. And it's just kind of fun to do. If a person has their ECG taken and you get something like this, something's not quite right. Look how extended, how elongated this QRS complex is. It should be this, shouldn't it? Very narrow. Look how it's elongated here, right? Well, this gets back to a potential issue in those right and left bundle branches. Remember, they came down from the interventricular septum.
The scar tissue you were talking about?
Did say it again?
Like if there was like a previous like heart attack, like the scar tissue.
Right. If there was a heart issue, whether it was due to a heart attack or maybe a congenital heart problem that the baby was born with, that can happen too. There's a whole host of things that could influence the pathways. But in this case, an elongated QRS complex would be an indication that there's something impeding the speed of the impulses as they come down the interventricular septum and then head up into the walls of the ventricles. And if you see something like this, call your doctor. You wouldn't be able to call your doctor if you were experiencing that. Does you see anything that looks like a PQRST there? Oh, I don't see anything. This is the situation where the person is having a myocardial infarction, more commonly called a heart attack. So what are you going to do when you see somebody? If you did see somebody, you're the ECG, you're the paramedic. You hook, Aunt Mabel up. All of a sudden, blip, 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 across your screen. Being the trained paramedic, Sadie's going to grab her 2 paddles, put some goop on the 2 paddles, yell to all of her aunts who are gathered around Mabel, get back! You're going to put those on Aunt Mabel, and you're going to give her a zap. Now, we have these machines here in many of the buildings at the college. You may or may not know that, where anybody, even if they're not, Red Cross certified, it's I've never done it, but apparently it's quite easy for the average, Joe public to grab this if they see somebody who's in need of a defibrillation. So we're going to defibrillate the heart by shocking it, and hopefully we get it back into a normal rhythm.
When I I used to be a lifeguard, and we had to use one like for training or whatever. It's like you put it on there and it detects what the person needs, and it like a voice comes up and it says like, this person is in VFib, like press, put the paddles like here and here, and then like you press the button and it walks you right through it.
That is so great. Wow. Wouldn't it be interesting to know, like on a daily basis, how many people are saved in the United States just because of this machine? I mean, it's really amazing. Yeah.
Yeah, we had this happen last year at my high school. A lady at a basketball game, she started to have a heart attack.
Really?
Yeah, it was. So our gym teacher had to do it, and yeah, it was cool.
You watched this whole thing happen, huh?
Yeah, it was like right in the middle of a basketball game.
Really?
Mm-hmm.
And she lived?
Yeah.
Oh my gosh, what a great story. Wow.
Yeah, and like our gym teacher teaches like the course, like the yeah. So it was kind of cool. I'd like to see him in action then with it.
Boy, do you think you guys could step up and do that kind of thing? That's pretty brave. But
leave it to him.
You just jump in there and you just do it,
Mm-hmm.
Yeah. No, that's very good. All right, so there's the paddles, and of course this is a more regulated sort of event. This is person's having open heart surgery, and they've pretty much slowed the heart down or stopped it to do the surgery, and now they're actually starting it back up. And they're not going to give as big a shock as you would to Aunt Mabel. You're just giving it a small little zap, and then typically the heart will just kind of begin to beat normally. Yeah, but those are the paddles. You can kind of see how they're putting on both sides of the ventricles. Yeah, it's pretty cool. All right, so there's a long explanation page to your question, I guess. But I think it's important stuff. How about other questions? You're just probably getting into chapter 15 now, aren't you?
Yeah.
So John's back from Ellicottville.
Yes, I am.
How about heart anatomy? Are you okay with the heart anatomy? Do you want to review that? I don't know where you guys stand on the heart, the various chambers, the valves.
That'd be beneficial for me, I guess.
Okay.
I just don't know how far along everyone else is, but I was just focusing more so like on like the blood and stuff.
Yeah, sure. You obviously A lot of people maybe haven't even started cardiovascular, although I don't hesitate. Don't wait too long. It's a pretty big chapter, and the lymphatic, likewise, coming up. Next week is a more challenging chapter. So,
Okay.
so let's go back to the heart. Do you all see that slide on your screen? Okay.
Yeah.
So here we've cut away part of the heart to reveal several of the underlying valves. Obviously in yellow, I've highlighted the two AV valves, or atrioventricular valves, the tricuspid on the right, between the right atrium and right ventricle, and the mitral or bicuspid on the left, between the left atrium and the left ventricle. Both the AV valves have chordae tendineae, which connect to papillary muscles that come off the walls of the ventricles. And you saw those up close and personal last Wednesday when we did the deer heart dissection. You can see the two large veins bringing oxygen for blood into the right atrium. This is the superior vena cava. This is the inferior. You remember those words from the second lab, superior meaning up, inferior meaning down below. Behind the superior vena cava, we can see the right pulmonary veins, which are bringing oxygen-rich blood from the right lung toward the left atrium. And here's the two left pulmonary veins that come from the left lung. They likewise dump into the left atrium here. You don't see the openings from the right veins. They're hidden underneath the pulmonary trunk, but they're going to come in here like these two have, and that's where the blood initially goes, right? This, of course, is the aorta, which comes up in arches. So you hear about or read about the arch of the aorta. You can also note the brachiocephalic trunk right here, and the left common carotid here, and the left subclavian artery there. They're delivering oxygen-rich blood up into the head and neck and into the shoulders, arms. Okay, are we good with this diagram?
Can we talk about why the right auricle and the right atrium look like that? Like why they're just like that weird purple like blob on the side?
Yeah. So let's see if I can find you a photograph. Maybe it's well, okay, here's not a bad one here. Now this is a pickled human heart, or preserved, I should call it. Not pickled, it's pickled. So here is the right auricle. Here's the left, a piece of the left auricle. We don't see the whole thing, it's kind of hidden from view. So when we use the word auricle, which means ear, it's simply the external part of an atrium. You cut through the right auricle last week and made a midline incision down toward the apex, remember? And then you did the same thing on the other side, remember? So when you cut through the center of this auricle, you cut into the atrium. So the only difference between the term auricle and atrium, in my mind, is the auricle is what you see when you look at the heart from the outside. It looks like an ear. What's inside the ear is the atrium.
So the atrium's the inside of the house, and the atrium and the auricle is the siding.
Yeah, that's right. That's right. That's a good analogy. Yep. It's exactly what I'm saying. Don't let that confuse you. Although, they do use those two different terms, with, I would say, the term atrium used more widely than auricle. Yeah. Okay, so these slides just kind of lay out the different chambers. So here's what we looked at a moment ago, and now we're just focusing on a particular set of structures, which I've already talked about. So I won't, talk about that right now. Here we see one of two semilunar valves. And of course, this is the pulmonary semilunar valve, which is taking blood toward the lungs. So just superior to that particular valve is the pulmonary trunk, which splits into the left and right pulmonary arteries. They are taking blood where? Come on, you should know this. If it's oxygen poor blood and it's leaving the heart, do you want to take it to the muscles? No.
No.
Where do you want to take it to get it oxygenated?
The lungs.
Right, the lungs. So the blood here is going to the left lung. The blood here is going to the right lung. You might want to run off that heart diagram that I have posted in Blackboard and label a lot of these structures that I'm pointing out, and then do a flow chart of the blood flow. Maybe start here in the vena cava and work your way through all of the different chambers and across the various valves until you make your way back to the vena cava. That would be a really good preparation for the exam in a couple of weeks. Not only know the heart anatomy, but also be able to trace general blood flow throughout the heart. And we can talk about that in just a minute too. Now, if I cut away this pulmonary semilunar valve and a little chunk of the pulmonary trunk, I can see now the other semilunar valve. This is the aortic semilunar valve, which you found that last week too. I pointed that out. Note that these two semilunar valves lack chorditendiny. They were just these three little semi-transparent, strong little valves. Remember me coming around and showing you those? Yeah. Okay. These are just some obvious photographs from a dissected human heart. This is a fresh heart because you can see how red the myocardium here is and the interventricular septum. The fact that it's bloody means it was just obtained from a fresh cadaver. And this is just zooming in on some of the chorditendiny and the papillary muscles. I know that this is the right ventricle here because of how thin the wall is. Here we're looking down from above onto a preserved human heart. And we can see the two semilunar valves, and I can see the two AV valves. It's been cut like across, like right here. So imagine this plane being twisted or turned, and now we're cutting it more horizontally, like right about here, I guess. Yeah. And then that would reveal that particular view, looking down from above. So this person's holding the heart by its apex, right? So it looks like a small heart to me too. It's awful small. These are likely coronary blood vessels. These holes leading, these are the lumens of some of the major arteries or veins. I can't tell which those are. There's another one here. Some more over here. This is a figure that came from one of the exercises we look at in lab today. Remember, this is showing both pulmonary and systemic circuits, just the general layout. This is an excellent, excellent, excellent diagram to look at. It has the heart anatomy. It shows the pulmonary and systemic circuits in a very general way. This is super excellent diagram to spend some time with. Excellent. As you look at this, at first it looks a little intimidating, but remember, this is just plumbing. That's all it is, plumbing. complicated plumbing, but plumbing. And again, there's a video here. If you want to watch it, I can play it. That kind of talks about the two circuits. Have you watched this yet? No? Let's play it.
The right side of the heart produces pulmonary circulation. This is the movement of deoxygenated blood.
Now you'll notice that they're coloring the oxygen-rich blood in red and the oxygen-poor blood in blue. Now they just use the word deoxygenated, which we said is really not a good term to use because that infers no oxygen. But even oxygen-poor blood has some oxygen in it.
From the body through the right atrium and ventricle, out through the pulmonary artery and to the lungs. Blood oxygenated in the lungs alveoli returns to the heart through the pulmonary veins. The left side of the heart produces systemic circulation. This is the movement of oxygenated blood returning from the lungs to the left atrium and ventricle and out through the aorta to be distributed to the rest of the body.
Yeah, it's a very, very general video. It doesn't really get into much detail, but it's not bad. So here's that flow chart that I was saying sort of follows the blood flow from the vena cavae all the way through to the systemic circuit, which would of course lead back to the top. So you're just looping down if you want to, get an idea of the directional flow of the blood. And I've, put in here where these various AV valves are or the semilunar valves, just to give you a sense. So that also would be very, very good to spend some time looking at. Other questions? I get a sense you haven't had a chance to really study this much yet. Yeah.
No, I started working on some of the notes today in class when I like to end there.
Mm-hmm. John, have you gotten into cardiovascular? Just a little bit of it, maybe, huh?
Yeah, just a little bit, not extensively.
Yeah. I would encourage you to, maybe make a goal of trying to get through, let's see. I'm not sure how long the Zoom lecture is, but try to get up through blood vessels maybe by the end of the weekend or further. In other words, kind of make the best use of the time you have left. In 2 weeks we're done, and in that time we got to get through cardiovascular and lymphatic. So do not wait until the last week to do lymphatic. That's a challenging chapter. Try to get this cardiovascular done by the end of the weekend if you can. Actually, I mean the sooner the better. Not to rush through this. I'm not saying that, but if you look at the syllabus, and most people haven't been following this, but if you look at how much time that I kind of devoted to cardiovascular, it was literally a week and a half, or no, actually 2 weeks, almost 2 weeks spent on cardiovascular. If we had met, maybe not quite 2, but close to 2 weeks. That's how big a chapter it is, with a remaining 1.5 weeks on lymphatic. So, anything you want to ask about? Questions?
Cardiovascular. We're just gonna sweep through the whole chapter. It ain't gonna be like we're breaking it up like we did in 19. So 19.5, 19.6. Not like that, right?
You know, I don't remember exactly. Let me pull up.
Because that chapter is large.
I think we only did that because the quiz.
Mm-hmm.
Share screen. All right, so when we go to the content section here and we go to Zoom lecture recordings, and then we scroll down to cardiovascular system, which is here.
Mm-hmm.
There are 4 Zoom lectures for this chapter.
Okay.
So they are broken up. Yes, they are broken up into 4 lectures. And it's the first 4 listed here, okay? Now do make note, Sadie.
Yeah, I noticed that. Yeah, I noticed that today. I was like, 41.
Okay. And as I said, I just do not remember. So this first one's 41 minutes long, right? The second one is 44 minutes long. The third one is 47 minutes long. And the last one is 37. So, I broke it up into somewhat palatable bite-sized pieces, maybe too big a bite, I don't know. But, rather than one big, huge one, we've got 4 of them. So I think that's a little bit palatable, manageable. And I've also thrown in here, not that you have to watch these, but this is an hour plus video. Yeah, a little over an hour on cardiovascular that was done from a different community college. I posted this last spring. I found it. I really liked how they covered it. So I put it up there. You don't have to watch it if you don't want to, but it's there. And I don't think you have to watch the whole hour long. You can pick and choose if you want to just hear a different approach to how somebody would teach it. And then this section is specifically talking about what we just talked about earlier today, and that is cardiac conduction, ECG, and regulation. The regulation of the cardiac cycle, that might be an interesting segment to watch. This is going to be about a half hour long, I think, too. So and then we've got angioplasty. Oh, here's the heart diagram for labeling. I was telling you about this. You can print it off and you can label the different chambers, and I think that's really quite nice. This would have been nice to look at. Freya referenced this last week when she was talking about the dissection. And then this walks you through the heart model. So just know that those are there should you want to watch those. This angioplasty is a technique for opening up partially blocked coronary blood vessels. Have you ever heard of this angioplasty? Yes. This is like, I don't know, less than 10 minutes long. Oh gosh, it's like 1 minute long. I thought it was longer than that. Anyway, it talks about the technique. It's pretty cool if you're interested in watching that. And then for the lymphatic system, which we're finishing up the semester with, there's probably at least 2 or 3 videos here. Yeah, there's 3 different lectures here. Now again, I'll just remind Sadie to look at the fact they're starting at 38. And then here you got to kind of scroll between those 2 and so on and so forth. These I recorded last fall. I think. So. All right. Any questions? Comments?
Now, any questions I have, I'll just call Sadie.
How much are you paying her an hour?
But,
I didn't bother her too much this last go around.
yeah, I noticed you didn't text me or call me at all yesterday.
Yeah.
Did you
'Cause I
give
think
him your cell number?
Yeah, we all have like each other's numbers.
Oh boy, you're brave. He'll call you at 3 in the morning.
John, I think the latest is like 11, but we were both up studying, so.
Uh-huh. Yeah. Now you guys could actually Zoom. You get a free Zoom account.
They've done that. Yeah, we have a group chat.
A Zoom.
Mhm.
Oh yeah, great. Who all meets then? You and
It's like Freya, Jolene, my Vay's in there, Kiray,
uh-huh.
yeah,
I'm not sure.
Beth's in there, Maddie, yeah.
It's just a little too active for me.
I know John normally just texts me.
Yeah.
There's too much going on.
Mhm.
Yeah.
Well, I'm almost done with your thing. Not going to show you yet.
Oh, that's the paper? You mean?
The painting that I'm doing for you.
Painting?
Yeah.
Oh, did you?
Yeah. Review.
Oh yeah, you were telling me about something like that, weren't you? Like I don't know, a month ago?
Yeah, like 2 weeks ago, I think it was. I'm just still doing. I just have so much stuff to do, but I will get it to you by the last class.
Oh wow, now you got me really interested. What could it be?
I love it. I sent it to Kira and she thinks it's so funny. Yeah.
Okay, great.
Yeah. I think it's
I
funny.
can't wait. It's not
So,
gonna be
yeah.
embarrassing or anything, is it?
No.
Oh, okay. All right.
No, you're good. Yeah. So yeah, my only questions really are like where I'm at grade wise right now.
Okay.
Yeah.
Oh,
Okay,
I-
let's
Drop the one quiz grade.
right. I just did that the other day. Okay, so so let's see. John, do you want any other questions answered?
No, I'm good.
Okay. I guess if I agree with
Don't
you,
flash nothing like this.
oh, that's cute. That's funny.
All right, guys. I'll see you.
Okay, John, have a good rest of the week.
Yeah, you too.
All right. 29 plus. Of course, I don't have the test done yet.
Yeah. I think I did pretty decent on it, but I thought I did good on that one quiz and I got a freaking 60. I just mixed stuff up.
Uh-huh. So we dropped this a 6 in the lecture quiz and an 8.5 in the lab quiz.
Mhm.
And I'm going to just double check my math because I always want to double check my math. So I'm coming up with a 349.5. Now, I'm going to give you 20 out of 20 for the instructor evaluation. So that really, that bumps you up to 369.5. Now that's out of how many points? Well, we had 40 points of lecture quizzes. We had 160 points of lecture exams, so the first two. We had a 30-point chemistry exam. We had 5 lab quizzes, each worth 10, for a total of 50. And then the 2 practicals worth 110 plus the 20-point instructor evaluation. Let me double check that because I come up with 410 points. 160, 30, 50, 110 and 20. Yeah, 410. So if I take 369.5 divided by 410, that comes up to a 90%.
Yes.
Yep. So if you did well on today's test, and let's just say you got a 90, just pick a number.
Mhm.
So that's going to keep you at that 90 average. And then the only other thing left is the practical, right? So if you were to get, you know, if you were to get 54 or higher out of 60, that would maintain your 90 average. And you'd be exempt from having to do the final. You already know this, I know you do,
Mhm.
right?
Mhm.
Yeah. Um, if you want, I can email you your exam score when I get it done.
Yeah, I was gonna ask you.
Or I can wait.
No, I was gonna ask you if you could do that.
Sure. Yeah, I can do that. I'm
Okay.
sure you're wondering. So, yeah,
Yeah.
I'd be happy to do that. I can't tell you exactly when I'm going to have them done. I'm not going to, like drag my feet, but it'll be sometime this weekend. And I'm more on the earlier end of it if I can help it. I'd like to get it out of the way.
Mhm.
And it's supposed to be kind of nasty weather the next few days. So it's not like I'm going to be outside doing stuff. So,
Gotcha.
yeah.
Yeah. I've just been trying to keep it up, but like
Yeah.
I've just been like psyching myself out. So
Yeah. Yeah.
yeah.
Well, all you can do is your best, and nobody can ask you to do any more than that. So, don't beat yourself up over it. I mean, I know you want an A, and you really are deserving of an A. I hope you get it. I really do. Are you doing a paper?
No,
Oh,
I'm terrible at writing. I was like, not even gonna bother with it.
oh, uh-huh.
Yeah. I'm
Okay.
taking English this summer. So
Comp 2?
yeah.
Uh-huh. Well, just know that the more you do it, the better you get at it, right? Like anything. And if you're in a situation like you are in this course, and if for some unknown reason you fell below the 90 average going into the final and you had to take the final, but you had done the paper and did reasonably well on it, it could have set you up grade wise in a good place. I'm not trying to pressure you or say you made the wrong decision. Don't get me wrong. But I'm
Yeah.
just saying down the road, just because you're not good at writing, you know, you get better as you do it, right?
Yeah. Yeah.
But
I don't know. It's just like chemistry is like cracking down right now. So I've
yeah,
been doing like a chapter a week and then
yeah.
I don't even think I probably would have had time.
Oh yeah, sure. You're busy. I know you're busy with stuff. What chemistry are you doing now?
It's just Gen Chem with Damon.
Chem 2.
The first one I'm taking Chem 2 the summer.
Oh, okay.
Yeah, so I'm taking that starts May 19th and goes to June 30th. And then I'm taking English the rest of the summer.
Oh, wow. You're going to be busy this summer, aren't you?
Mm-hmm. I just wanted to get it out of the way.
Yeah, that's a good idea. It's
Yeah.
less to have to worry about next fall, right?
Yeah. And then I'm taking A&P2 and Bio 1 in the fall, as well as a history class and then a yoga class just for fun.
Good. Yeah, that's great. Yeah, that's great that you're taking yoga. A lot of people enjoy taking that course.
Yeah, I just figured get me at the gym. So
Yeah, right. No, that's good.
Mhm.
Okay, well, I will be in communication with you, and let's hope you did good.
I think I did pretty good. I think I know I got the one wrong about the leeches. I couldn't remember if it was the maggots or leeches. So I put maggots because I couldn't remember the name.
Uh-huh.
But I knew it's leeches now that I looked it up. So I know I got that one wrong.
Well, just one question.
Yeah. So and that one's out of 100 points. So if it's just like one question, it's still in the 90s. So
Yeah.
so I think I did good though.
Good. Well, it's good to leave a test and feel good about it, as opposed to leaving a test and knowing that was not pretty.
Yeah, no, I've been pretty good on like all of them. I don't know, like yesterday, Key she got out of work at like 6 and like still needed to like do the blood. So I just like sent her my notes just so like that would help her. She's like, holy crap, you take so many notes. I was just like, yeah, I literally write down like everything though. So
Well, you can be a role model for a lot of those students because they see what it takes. A lot of them don't know how to study. You've done this now with enough people in this course that the abilities range wildly and the preparedness ranges wildly too.
yeah, like I just tell them, do flashcards. Like, here's some.
All
AUP. This is all of them. Like, I just tell them, do the flashcards, study with someone else, do all of the notes, like watch your videos. I don't know.
Did you just learn to do that from this class, or had you done that in other classes?
I used to do this in high school. I was the same way. If it was like a literally like a 3-question quiz, I would study like everything. So
Yeah. So you sort of have the drive and you know how to study independently, and so you have those skills. A lot of students don't have those skills. My kids had those skills too, and as I may have said, when they were in high school, they had homework every night for like 3 hours, and I used to think at times that was really so unfair to burden them with so damn much homework. But I'll tell you what, when they got to college, they did what you did, and if they had an instructor that just didn't really teach very well and the onus fell on them to learn it, they had the tools to learn it themselves and they did okay.
Mm-hmm.
And you got to have those skills, I think, or try to promote those in your life because it can really pay off.
Yeah, because like I don't like getting to like a test or a quiz and like not knowing what's on it. Like I need to like be good with it. Like I don't like looking at a question being like I have no idea what this is. Like that just stresses me out so much.
Yeah, right. No, I totally get what you're saying, and that's the way it should be.
Mm-hmm.
Yeah, that's good. Well, my Vay is joining us. We have a advisement session, so
Okay.
I
Well,
will
thank you for letting me know.
I will let you know. Okay. Thanks, Sadie.
Yes.
See ya. Bye.
Bye.
Hi, Maeve.
Hi.
How did you make out with your mom? Everything okay?
Yes, but we still in Buffalo.
Yeah. Uh-huh.
Yeah, today like the office like wait a little bit longer.
Uh-huh.
Yeah.
Well, you knew that could happen and was likely to happen. So
Yeah, I don't know why when you go to the office, doctor, sometimes you have to wait very long. And she's still in the office with my dad.
oh, uh-huh. What was her appointment at 2 o'clock or what time was it?
It's around 1. No, 12:30.
And it's 2 hours and she's still waiting?
Yeah, I don't know
Gee.
because we need the translator. Yeah, and sometimes they have to connect with the translator. And
Oh,
yeah, this office like because when sometimes we have the appointment, some office they have the machine for translate, some office they don't.
oh, I see. Uh-huh. Right. That really makes things complicated, and doesn't it? It makes it hard.
Yeah,
Oh,
sometimes I cannot translate because the disease and something the doctor say I don't understand.
yes. Yes. I understand what you're saying. You do your best, but you are limited as to how much you can translate. Yeah.
Yeah. Sometimes I understand what he's saying, but when my mom tell me and I cannot translate for her to him. So
Yeah. 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 I understand. I'm sure that's very, very frustrating for you and your mom and your dad and even the physician sometimes because they want to help.
yeah.
Yeah. Well, I hope that you get a translator there soon so that you can get home.
Yeah. Maybe like we wait because they don't find any translator, and then they take another patient until they find the machine or something like that, and we can
Sure.
move in. Yeah,
Yeah. Well, I guess you have to expect that that it will take longer than you think.
yeah.
Yeah. Okay, so we're here to talk about, um,
Oh, you still recording?
I am. So I have to stop recording and we will meet back again. So you'll have to go back into the room, okay?
Oh, okay.
Yeah, thank you for reminding me. I'll see you in a minute then.